In the previous lesson, we've created a new event store and integrated it with our application. Dispatched events are now automatically persisted in the event store. But that's when the magic stops. Conceptually, our events are flowing out of the application, but they're not flowing back in. This would be even easier to see why it's happening if we had a separate application for writing and reading. Not to worry, we'll get things working here in just a moment. Now, when it comes to processing events, there are two different strategies, push and pull. In this course, we're going to implement the push strategy with collection watchers, meaning we're going to watch for new MongoDB documents or events. Whenever a new document is inserted into the collection, our application will receive a signal with the new document payload passed in with it. Then, we can use that document to recreate the event instance and add it to the event bus. In the pull strategy, on the other hand, instead of subscribing to the collection watchers, we would periodically poll the database for new events. To determine what events are new, we would need to keep track of the last processed event, for example, by storing the version of the aggregate in the read database. Then, we would query the database for all events with a position greater than the version of the aggregate, which corresponds to the last processed event. Alternatively, we could use a cursor-based approach and just track the number of events processed. This is a slightly simpler approach, as our application can process events at its own pace, but it's also less efficient, as we're constantly querying the database for new events, even if there are none. Whether you choose the push or pull strategies depends on your use cases, the frequency of events, type of the database you're using, whether it supports change streams or not, etc. But in our case, let's jump right in and implement the push strategy with collection watchers. Let's start by creating a new file called eventsbridge.ts in the event store folder, and let's add the following code inside. And let's break it down line by line. Our EventsBridge class implements two interfaces, onApplication Bootstrap and onApplication Shutdown. In the onApplication Bootstrap lifecycle hook, we're creating a new change stream and we're subscribing to the change event. Whenever a new event is inserted into the event store, the change event will be emitted and we'll call the handleEventStoreChange method. In the poll-based approach, instead of using a change stream, as we're doing here, we would periodically poll the event store for new events. To keep track of what events we already processed, we would need to store the last processed event or cursor in a separate collection. Back to our code, in the onApplication Shutdown lifecycle hook, we're just closing the change stream to prevent memory leaks. Inside the handleEventStoreChange method, we extract the inserted event from the change stream insert document object and we're deserializing it. Note that the change stream insert document object exposes the TXN number property, which represents the transaction identifier. If you need multi-document transactions in your applications, you can use this property to achieve atomicity. For example, if we inserted multiple alarm-related events as part of a single transaction, all events would have the same transaction number, or TXN number value. Now, before we can push the event to the event bus, we need to deserialize it. So let's create a new file called eventDeserializer in the deserializers folder. Let's go ahead and add the following code. This simple class takes an event and deserializes it by mapping the event data object to the corresponding event class. For example, if we have an event with the type alarmCreatedEvent, we'll map its data attribute to the alarmCreatedEvent class instance. Let's declare the first missing method, getEventClassByType. In this method, we return the corresponding class reference based on the event type. As we can see, this isn't the most scalable approach, but we'll show a better one later on. And finally, let's declare the last missing method here, instantiateSerializedEvent. This one might be a bit confusing, so let's go ahead and break it down. We have two input arguments here. The first one is the event class reference, and the second one is the event data object. The object.create method creates a new object with the specified prototype. In our case, the prototype object is the eventCLS.prototype. Then, we're using the object.assign method to copy the properties from the data object to this newly created object. Finally, we're returning the new object, which is an instance of the event_cls class. This is all required so that we can push the event to the event bus. The event bus expects an instance of the event class, not just the plain object, to recognize what event handlers to call. Great, so let's save our changes, head over to the events bridge.ts file, and let's inject the newly created event deserializer class. With this dependency injected, let's scroll down to handle event store change and let's deserialize the event and push it to the stream. And that's it. We've successfully implemented the push strategy with collection watchers. Before we test everything out, let's make sure we register our new events bridge and event deserializer classes in the shared infrastructure module. Last but not least, let's open up the alarm created event handler and update the handle method signature to take the serialized event payload of type alarm created event as an input argument. Let's also update the iEventHandler type argument to use this same type. The reason why we're doing this is simple. Our event handlers receive deserialized events now, but not real domain event instances with value objects, etc. That's why we also have to tweak the execute method just a little bit. And voila, we're done. So let's go ahead and test everything out. Let's head over to our terminal and in a separate tab, let's create a new alarm. Let's switch to the other terminal window, and as we can see, the event handler has been successfully invoked. Fantastic. Just to double check if our newly created event is also reflected in the read side database, let's try and fetch all alarms. And as we can see, our newly created alarm is there. Great. So now that we've come full circle, we've fixed the missing link from the last lesson. We're now able to create events in our event store, but now we can also access that information on the read side of our application. We're making great progress.